Hello and welcome to this session on understanding the Java virtual machine and low latency applications. My name is Simon Ritter and I work for Oracle as a technology evangelist. Firstly, I have to put in this slide, which is basically our safe harbor statement. When we look at applications, people always want fast applications. But what does fast really mean? There are different ways of interpreting what people mean by the term fast. Firstly, there's I want the answer as fast as possible. And then secondly, there's I want all the answers as fast as possible. So in one, we want a single answer as quickly as possible, and in the other, we want lots of answers as fast as possible. And these are very different approaches to the idea of what we mean by fast. The two goals themselves are somewhat orthogonal or different in terms of a programming perspective. If you want to achieve one answer as fast as possible, your approach is going to be different to if you want all the answers as fast as possible. If you want just one answer as fast as possible, then we're talking about a low latency application. We want the response time to be as fast as possible. If we want all the answers as fast as possible, we're talking about high throughput, because the latency for a single answer in amongst all of the answers could be higher. But so long as all of them are processed in the shortest possible time, we're not concerned about how quickly a single result takes to be processed. In the case of wanting one answer fast, then we're talking about low latency. And that's really what we're going to be talking about in this presentation, is how to reduce the amount of time that it takes to get a single answer. How can we make things as have as low latency as possible? One of the first things we've got to look at is the fact that in Java applications we have a Java virtual machine. And Java virtual machine will have a number of performance considerations associated with it. Probably the biggest is the fact that it is, by its very name, a virtual machine. We're not dealing with a physical machine in the sense that we're interacting directly with the hardware of the machine. When you compile a Java application, what you're generating is bytecodes which are for the virtual instruction set of our virtual machine. They may match in some ways to the native instructions that are used by the platform that you're working with, but the chances are that they won't all map one-to-one. So there has to be some conversion from the bytecodes that are generated by the Java compiler into the necessary native instructions for the particular processor, the particular bus architecture, and so on that you're using. And similarly, for the operating system, there will be a number of library calls that you need to use. And again, the bytecodes need to be converted so that you make the appropriate library calls for the operating system that you're using. How this happens can be in one of two main ways. You can use fully interpreted, where every single bytecode is processed as it's used and is converted to the necessary instructions. Every time you do the same thing, you have to reprocess the bytecode and make the conversion. So if you're in a loop, every time you go through the loop, you have to make those conversions every single time. The other approach is to use just-in-time compilation. Rather than compiling everything ahead of time, where we would compile all of the code into native instructions and then run it as a native application, what we do is we allow the application to start running, we interpret the bytecodes as the application starts working, and then we identify hotspots within your application. Where you start running a loop a number of times, the virtual machine can identify that and say the instructions within that loop can be compiled into native instructions, such that as you iterate through the loop a number of times, rather than converting the bytecodes into native instructions every single time, you get to the point where they're compiled into native instructions, and then for subsequent iterations through the loop, they'll be executed as native instructions, giving you a much faster processing time. The other big thing with Java is that, unlike a lot of native code, it deals with automatic memory management. If you want to create an object in Java, you use the new operator. So you instantiate an instance of a class and create an object. The Java virtual machine is responsible for allocating the space for that object. You don't have to do that. You don't have to call malloc. You don't have to allocate the space for your object. So Java will take care of that. Java virtual machine will do that for you. The other thing is that the Java virtual machine has a garbage collector. And what this does is it eliminates the need for you as a developer to programmatically free up the memory that you're using. So unlike other languages like C++, you don't explicitly have to deallocate space associated with objects. The garbage collector will keep track of all the references that you have within your application. When you stop referencing an object, and so you're no longer using that object, the garbage collector can detect that, and during a garbage collection cycle can then reclaim the space. How that happens is down to the implementation of the virtual machine and what particular algorithm you're using. We'll talk a lot more about this as we go through. The other thing with the idea of automatic memory management is that by doing it this way, we also don't have any explicit pointer manipulation. Again, unlike C and C++, you can't actually talk about a physical or even virtual memory address and manipulate that. You can't store things in a physical memory address or a virtual memory address. And this makes programming in Java a lot safer because you don't have the issues of incorrect pointer arithmetic, freeing up space that you don't own, referencing areas of memory that you don't have access to, and so on. Java, right from the very beginning, has been designed to work in a multi-threaded environment, and we provided the capabilities within the libraries to enable you to do this. So you have the thread class, you have the runnable interface, you have the ability to instantiate a new thread. That can allow the Java virtual machine to create a new thread and have your application have multiple threads all running at the same time. In order to allow you to protect data, so that you get consistency of data even when multiple threads are potentially trying to access the same piece of data at the same time, we have the idea of locking. Each object has a single monitor associated with it, so that when you use the synchronized keyword for a method or a block of code, then you acquire the monitor and you can lock that particular object. Some of the more recent inclusions in Java SE5 and beyond have provided higher level locking constructs, so that you have concepts like semaphores, you have things like read-write locks, mutexes, and so on. What this allows us to do is to provide some programmatic locking, some automated unlocking. So you can provide locking on objects, you can provide locking on data structures, and so on. And then depending on what approach you use, the unlocking can either be automated, so if you use a synchronized block or synchronized method, then you automatically release the lock when you exit that piece of code. Or if you're using some of the libraries, then you explicitly have to unlock your code as well. All of these things have performance considerations because they introduce changes to how the system works which can affect how your application will run. Let's look at the idea of an application stack, because as with many things in computer science, we can take a layered approach to how we see an application running. At the bottom, we have our physical hardware, the CPU, the memory that we have, the bus architecture that's being used, caching, all of those very low level system-specific hardware pieces that are in our applications platform. On top of that, we have an operating system, and the operating system is the software that enables us to not have to worry as developers about which physical memory address we need to talk to in order to access a particular device. It enables us to be isolated from all the complexities of how we communicate with things like the network card, how we deal with the virtual memory address translation hardware in the system. All of those things are isolated from us. And the operating system provides a lot of other functions, a lot of higher level things that are very important from the point of view of running applications. You will have potentially many applications running at the same time on a single system. And it's the operating system that handles the scheduling of those applications and the threads within those applications. And by using different scheduling algorithms, we can use different approaches to how to make things as fair as possible so that different threads get access to the system and are not blocked continuously. We can implement priority systems to give certain threads higher priority and get more resources than others, and so on. So the operating system allows us to do all of those types of things. On top of that, we have our Java virtual machine. We've already talked about some of the things that the virtual machine does in terms of memory management, thread synchronization, and so on. And really the key point about this is that the virtual machine is isolating us as the application code and the developer from the operating system and from the hardware. So when you write your Java code, you don't need to worry about whether you're implementing it on Linux, whether you're implementing it on Windows or Spark, whether you're implementing it on Intel hardware, ARM-based hardware, whatever. So this is where the famous write once, run anywhere approach has come from. So you write your application in Java, and it's the Java virtual machine that handles converting that into the necessary instructions to run on the platform that you're actually using. On top of that, if you're using something like an enterprise Java application, you may well have an application server, something that provides containers, the ability to manage resources, the ability to provide connections to databases, to transaction monitors, to security systems, all of those types of things that are required for enterprise class applications. This is optional, obviously, because many Java applications don't require an application server. And then finally at the top we have our Java application code. The code that we as developers write, what we compile into our Java classes, create our jar files. If we're developing enterprise applications, then we'll be creating war files or ear files. But it's what we're actually developing in terms of the functionality of our application. So the important thing about this stack is how we can look at it in terms of the effect that we can have by tuning different parts in changing the way that our application will run. And effectively, what we can say is that from the bottom upwards, we'll have more impact by making changes the further up the stack we go. If you think about it, it's very difficult to make changes or have an impact in terms of hardware. Yes, you can add more memory, yes, you can add CPUs, but beyond that you can't really change anything in terms of the way the hardware actually works. Operating systems have the capability to change certain parameters about how they work, but mostly from an operating system perspective, there are very few things that you would need to change, and if you do change them, it won't have a significant impact on how your application actually runs. Within the Java virtual machine, there are many options that you can use to change the way the garbage collector works, the algorithms, the way that the just-in-time compiler works, threading, all those types of things. So there's lots of things that we can do in terms of tuning performance within the Java virtual machine. Similarly, for the application server, there are various things that can be changed to tune the way that connections are handled, pooling, all sorts of things like that. And in our Java application, clearly we can change the way that our application works. We can take a different approach to algorithms to make them more efficient or do things in different ways. And that will have the biggest impact on how our application works. From the point of view of our application, we can have the biggest impact in terms of the application code. Beyond that, we're looking at tuning the Java virtual machine. We don't really need to worry too much about operating system and hardware. So we want to look at application code and we want to look at the virtual machine. In the rest of this presentation, I'm not going to talk about application servers specifically. We're going to be talking about how the Java virtual machine works rather than enterprise class applications specifically. So first of all, let's talk about memory management and how this works and the impact it can have on latency for our applications. What we need to do is look at the layout of the heap space that is being used by the Java virtual machine. Now what we're seeing here is the layout for the heap in the HotSpot virtual machine. There are other implementations of the virtual machine which may use slightly different approaches, but from the point of view of the Oracle HotSpot implementation, this is what we use at the moment. So you can think of the heap being broken up into certain regions, and we use a generational approach to the heap space. So where objects reside is based on how long they've actually been in existence. At the bottom, we have this purple area called the permanent generation, and effectively you can ignore this. This is used for virtual machine, class metadata, objects, things which you don't access directly from within your application. The only way you would access things in the permanent generation is if you're using reflection and you need access to class objects or method objects, things like that. And in fact, for JDK8, the plan is to remove this generation completely. So what we really need to focus on is the heap space as would be used by your application directly. And this is broken up into two regions. You have the young generation, which is the lighter blue section at the top, and the old generation, the darker blue section at the bottom. Within the young generation, we actually break this up into three regions, which are effectively two regions, because you have the Eden space and then you have two survivor spaces. What this allows us to do is to change how we allocate space for objects and also how we reclaim space from objects that are no longer used. So if we look at what actually happens, when you allocate an object, this will most of the time, in fact almost all of the time, will be allocated in the Eden space. And so you will allocate space via the virtual machine for your object, and then you can write whatever values into your object and they will be stored in Eden space. When Eden space fills up because you've created a number of new objects and more space is required, we do a minor garbage collection. Minor garbage collection requires the moving or copying of all live data that is still in the Eden space into one of the survivor spaces. All live data that is in one of the survivor spaces is also copied to the other survivor space unless it has been in the survivor spaces for a predetermined length of time. When objects become old enough, they are promoted into the old generation. So they then become part of the old generation and space is allocated for them there. The important thing about this is that by using this approach, we can take the different approach to the algorithms we use for allocation, we can take the different approach for how we do collection and so on, especially in the old generation. But really the key point here is that it requires us to move or copy objects from one area to another within the heap space. So during garbage collection cycles, objects are being copied and effectively moved between different areas of the heap space. The impact on us as an application is that we can't, from the JVM's point of view, allow an application to continue running whilst we're doing this copying of objects from one place to the other. Because if we have an object in Eden space and we're in the process of moving it to a survivor space, if application code starts changing values there, how do we know whether we've copied the right values into the survivor space? Or are we making changes to the survivor space as we're copying the object? It becomes very complex. So what we do to avoid that problem is to introduce a pause on all the what are called mutator threads. All the live threads that you have in your application are paused during a minor garbage collection cycle. This is where we get the problems of latency, because the way that that happens is non-deterministic. We can't predict when a garbage collection cycle is going to start, because we don't know how quickly you're going to allocate objects in your application, so we don't know at what point that will kick in. This non-deterministic nature is what affects latency, because we can tune things in terms of how our code works, and we can know specifically that it takes a certain amount of time for us to execute a certain number of instructions. And we can say that for a particular task it has a certain number of instructions, so it should take a certain amount of time to execute. But if garbage collection happens during the execution of those instructions, we introduce a pause which could be variable in length. And that variation in length is what introduces non-deterministic behavior in our low latency applications and can make latency longer than we would expect if there was no garbage collection involved and no pauses. So this is one of the things that we need to understand, and one of the things that we need to then approach in terms of how to tune both our virtual machine and our application code to minimize the impact of that. So, important concepts of garbage collection. First thing we need to understand is that the frequency of the minor garbage collections, which is where we need to move objects from the Eden space into survivor spaces and from survivor spaces into the old generation, is dependent on the rate of object allocation. The faster you allocate objects, the quicker you're going to fill up the Eden space, and therefore the more quickly you will need to have a minor garbage collection. Makes sense. Similarly, it's dictated by the size of the Eden space. The bigger you make your Eden space, the longer you'll be able to allocate objects for before you have a minor garbage collection cycle. If you make the Eden space smaller, you'll take less time to fill it up, and therefore how frequently minor garbage collections occur is dictated by the size of the Eden space as well as the rate of object allocation. How frequently we promote objects from the young generation into the old generation is dictated by several things. Firstly, it's dictated by how frequently we run a minor garbage collection cycle. This is effectively how quickly we age things. Because we copy objects from one survivor space to another, and we do that a certain number of times, the more quickly that we have minor garbage collection cycles happening, the more quickly we'll get through that number of copies between the survivor spaces, and therefore the more quickly we'll start promoting objects into the old generation. Similarly, the size of the survivor spaces will dictate to some extent how quickly we age objects. And the tenuring threshold, which is the number of times that we will copy objects back and forth, will dictate how quickly objects get promoted into the old generation. By default, that's 7. So an object will be copied 7 times between the survivor spaces before it gets promoted. The idea behind that is that it gives objects a chance to become garbage before they get promoted into the old generation. And we'll come back to why that's important in a moment. So, ideally, as little data as possible should be promoted into the old generation. What you really want is to keep everything in the young generation and promote as little as possible into the old generation. Anything that involves copying, either from Eden space into the survivor spaces or from the survivor spaces into the old generation, requires input and output and must, by virtue of the fact that we have to protect data, be stop the world. So it involves pauses, introduces non-deterministic behavior, affects the prediction of latency in our application code. Other important concepts of garbage collection is that the object retention impacts latency more than object allocation. So garbage collection only deals with live objects. If we don't have live objects in the Eden space, we don't have to do anything with them. We can effectively ignore them. So we only deal with live objects. Similarly, when we're collecting in the old generation, we only need to look at the live data that we have. So however many garbage objects you have makes no impact on how long it takes to actually analyze how much garbage you have. You're simply looking at the live data that's involved. So garbage collection is a function, or the time of it is a function of the number of live objects that you have, how many live objects you have to look at in order to detect all of the data in the application as it's running at that point, and also the complexity of that graph. What you will have in your application is references directly using the variables in your code to objects. Those objects themselves will then have references to other objects. The graph is the relationship between the variables that you have in your application through the different objects, through to the other objects, and all the continuous collection of objects that are live data. How complex that graph is in terms of the relationships between those objects, whether they're cyclic references, whether they're complex cyclic references, and so on, can have an impact on how long it takes to run garbage collection, and therefore will affect latency. Now, one of the things that we have to understand is that in terms of object allocation is very, very cheap. For the hotspot virtual machine, we're literally talking of the order of 10 cycles in common case, which is most of the time, to allocate an object. The reason for this is that we treat Eden space as a stack, and we have a stack pointer, and when we want to allocate space for an object, all we have to do is say, put the object where the stack pointer is at the moment, increment the stack pointer by the size of the object, and we're ready to start allocating again. So that's very, very quick and very, very cheap. Even in the case of multiple threads, what we do is we use thread local allocation blocks so that each thread can have its own allocation pointer, and we don't have contention over different threads trying to access the same pointer to allocate objects. So we're talking about literally 10 cycles for common cases. And if you compare that to the way that malloc works, you're talking about roughly 30 cycles even for the fastest malloc algorithm. So we're sort of 3 to 1 ahead just in terms of object allocation. With short-lived objects, reclaiming them is very cheap. And this comes down to the fact that we simply ignore them when we're doing a minor garbage collection. So all we do is we look at the Eden space, we look for the live data in there, and we copy those objects to a survivor space. So anything that's garbage, we simply ignore. We don't have to do any processing on it at all. When we've copied the live objects, we reset the pointer to the beginning of Eden space, and we've effectively collected all of those objects without doing anything to them. There is this thing called the weak generational hypothesis, and what that says is that for typical applications, most objects are very, very short-lived, literally of the order of a few million instructions before objects become garbage. Literally another megabyte is allocated and your objects become garbage. So most objects, 80 to 98% of objects, become garbage very, very quickly. And so if they die within the Eden space, it's very cheap to reclaim them. So what does this mean in terms of rules of thumb for approaches to low latency? Well, the first thing is don't be afraid to allocate objects if you're going to be disposing of them quickly. If you're doing intermediate results, don't worry about allocating objects and using them if you know that you're only going to retain them for a very short space of time. If you've got a loop and the object that you're allocating is scoped within that loop, you know that it's only going to exist for a short space of time. So the garbage collector can reclaim that space without any significant overhead. And because we know that allocating the space for that object is very easy, again, we know that it doesn't impact greatly on performance of the application. The other thing is that the garbage collector likes small immutable objects and short-lived objects. So anything that's immutable, can't change it, like strings, is also very good. As long as they don't survive a minor garbage collection, yep, that's all good, because we can use these things and we can take advantage of that in terms of the performance of our low latency applications. Try to avoid complex inter-object relationships. Now, this is a rule of thumb, and it's one of those things that's easy to say, but is it really easy to implement? The thing is that because garbage collection has to analyze the full graph of live objects and the references between them, the more, as I said, the more complex the graph of relationships, the more time it will take to do things. So it's something really just to think about and bear in mind when you're designing your application, is how complex you make the relationships between the different objects in your application code. If you can simplify it rather than using a very complex set of relationships, then that will help you in terms of latency. However, on the flip side of that, let's not go completely overboard. So don't allocate objects needlessly. Yes, it's cheap, yes, it's easy to reclaim them, but the more frequently we allocate objects, the more frequently we're going to do garbage collection, simply by virtue of the fact that's the way it works. Similarly, the more frequently we're going to do garbage collection, the more frequently we're going to be copying objects between the survivor spaces, and so the effective change is that we will be aging objects faster. Similarly, faster object aging means faster promotion to the old generation, and what we don't want is to really get a lot of data into the old generation. So more objects in the old generation means that you're going to have more frequent collections more compacting collections or concurrent collections, depending on how your old generation algorithms are configured. So ultimately, it's better to use short-lived immutable objects than long-lived mutable objects. And again, this is just sort of a rule of thumb, so it's not something to sort of think of, right, I must never use a long-lived immutable object. That's clearly not going to work. And trying to use only short-lived immutable objects is not going to work either. But it's something just to bear in mind when you're designing your code and you're thinking about how to approach different parts of your application code. So what we end up with is the ideal garbage collection scenario. What will be the best possible situation that we could have in terms of garbage collection? And what we're really looking for is an initialization phase where the application starts doing the work that it needs to do and builds up the set of data that it's going to work on. And what we don't want to have happen is for that set of data to really change a lot. So we want that data to be promoted into the old generation and then that to be a fixed size set of data that stays there and doesn't really grow very much. We can use lots of objects in terms of doing the work around that data so long as they never get promoted beyond the young generation. So what we're ideally looking for is no garbage collection on the old generation and only collection in the young generation, because minor garbage collection pauses are, on the whole, the fastest garbage collection that you'll get. In terms of how we can approach that, what we really want to do is start with parallel garbage collection. So we either use the plus use parallel old GC or plus use parallel GC options. And what this will do is it will enable us to do the fastest possible minor garbage collection that we can. Clearly that's limited by the fact that you would have to have multiple cores and multiple CPUs. Because if you've only got one core, one CPU, trying to do things in parallel isn't going to help you. It only works to your advantage if you've actually got the capability to do things truly in parallel. In terms of doing that, what we've done is to really try and improve the efficiency of the algorithms that we use. We use techniques like work stealing. We have made sure that the way that the work gets divided up doesn't have contention for data structures, so there's no locking involved, and those types of things. So we can make the best possible use of multiple processors when it comes to doing minor garbage collection cycles. If you are experiencing old generation collection, which is not unheard of, then for low latency applications, what you want to be doing is using the concurrent mark sweep collector. The idea here is that what you do is you actually do some of the garbage collection in parallel with the application code. So you're not creating very long pauses in order to do the old generation collection. Now that has a knock-on effect because the way that the concurrent mark sweep collector works is it doesn't compact the data in the old generation. And because it doesn't do that, you end up with the need for free lists in order to determine where the spaces are that you can put objects that are being promoted from the young generation into the old generation. The effect of that is that some of the minor garbage collection times can be a little bit slower because now you're having to manipulate the free lists, you're having to search for an appropriate size block, take that block off the list, use it, and so on. However, because we can hopefully avoid having to do a full compacting collection on the old generation, the downside of having slightly longer minor garbage collection pauses is very much offset by the fact that you're not having significant pauses for old generation collection. One interesting aside on the concept of concurrent garbage collection is that concurrent collectors require a write barrier in order to track potentially hidden live objects. This is because with the fact that you're having code executing at the same time as the collector, we need to track changes which are being made to objects as the collector is running. When we get to the point where we need to actually complete the garbage collection, we have what's called a remarking phase, and that will then take into account any changes that have been made whilst we've been doing the concurrent work. But from the point of view of tracking changes as we're doing the concurrent garbage collection, we need a lock so that we can track changes in terms of hidden live objects. Anything that involves a write barrier is going to introduce a performance overhead because you've got the concept of locking involved, you need to acquire the lock, you need to release the lock, and so on. Obviously, the overhead involved in that. Depends on the implementation. If you have a very efficient implementation of the locking mechanism, then you can have very low overhead. Things where the system is able to track the fact that the same thread is acquiring and releasing the lock on a particular object, then we can do things in terms of changing that into a no-op, and that becomes a very efficient way of doing things. So the impact of using concurrent mark sweep and the write barrier does depend a lot on the implementation. If we use a stop the world garbage collector, you don't require a write barrier because you're pausing all the application threads, you're pausing the mutator threads, and so there's no problem with objects being modified as the application is actually running and as the garbage collection is running. So for an ideal situation, we use the parallel garbage collector or the parallel old garbage collector, avoid old generation collections, and thus avoiding full garbage collection. Let's talk a bit about how we can be friendly in terms of our programming towards the garbage collector. We know the garbage collector is there. How can we actually help it to do its job by minimizing the impact of some of the things that we do in terms of our programming? The first thing to consider is the concept of large objects. Now, large objects are used very logically in a lot of applications, but what you need to do is consider how these things actually work internally. Large objects can be expensive to allocate. If they're very large, it may not be possible to allocate them in Eden space. It may not be possible to allocate them in a survivor space. So for very large objects, they get allocated straight away into the old generation. And again, if we're using concurrent mark sweep, we have free lists, we need to allocate and find a block of the right size and so on. So we're not using the fast path for allocating objects, we're not getting the advantage of this 10 cycles, 10 instructions to allocate an object. The other thing is that for large objects, it can be expensive to initialize. The Java specification requires that all of the bytes in a particular object are zeroed when it's created. So if you've got a very large object, there's an overhead in terms of actually going through and making sure that every byte is 0. Another thing is that the use of large objects can cause fragmentation in our heap. Once they get into the old generation, because we're having to fit them into gaps between live data as we allocate space for them, the heap can become fragmented. We can have objects dotted around the heap space, not contiguous in memory. The gaps between the large objects and other live data can become small enough that we can't fit another object into that, and so we lose the ability to use that space efficiently. So there's a number of impacts that using large objects, and a large number of large objects, can actually have on our application in terms of its performance with the JVM. So rule of thumb really here is to say avoid large object allocations if you can. Don't use this as a hard and fast rule. If the algorithm that you're trying to use and the problem you're trying to solve requires large objects, don't think I can't use them in Java. Just think about whether it's possible to use as small a number as possible, whether there's a different data structure you can use which maybe doesn't have so many large objects and so on. Certainly it's not so bad during application warm-up. If you want to allocate large objects that are going to be used for the length of the application, that's not such a bad thing. It's when the application has reached its steady state that you don't want to be allocating large objects. So here the concept of pooling can become important. You create a pool of large objects that you want to use during the application's run, and those can be allocated at startup time, and that way you have a steady state of data as the application is running beyond its startup time. Next thing in terms of garbage collection friendly program is thinking about data structures and resizing. There are a number of collection classes in Java which are backed by some form of data structure. Something like an array list, something like a vector, which has storage underneath it. When you create one of these collection objects, if you don't pass a parameter to the constructor, a default size will be created for you. And what happens is if you start adding objects to your array list, adding objects to your vector, and you need more space than it was initially allocated, the storage underneath needs to be resized. Typically it will double in size and more space will be allocated for you. Now that's invisible to you as a programmer, but can have a significant impact on the way that the system works because it's having to happen invisibly to you, the programmer. So if you know that you're going to be using a large number of spaces in a collection, which is such as an array list and so on, then it may well be better to size it accurately when you create it. Use the size parameter in the constructor and set it to be a good size so that it will hold all of the objects that you need. Again, you need to be careful with this because allocating lots and lots of objects where you're not necessarily going to use them all the time can be detrimental, because you're suddenly allocating space for a large number of objects and you're possibly not using all of that space. So you're wasting space in terms of memory resources. So as I say, resizing can lead to unnecessary object allocation, also contributes to fragmentation. This is a problem if we're using a non-compacting garbage collector, such as concurrent mark sweep. Object pooling is a very good technique. It works very well for certain types of objects. If you're going to use things like threads, if you're going to use things like JDBC connections, then pooling of those objects is very sensible, because if you're going to use them frequently, what you don't want to be doing is constantly creating those objects and then letting the garbage collector tidy up after you. So it's much better to use object pooling. But there are some things that you need to be aware of there, which is that if you have a large number of objects in your pool and you're not necessarily using them all, you're adding to the complexity of the graph of live data, you're adding to the number of objects that the garbage collector needs to visit every time it runs through its garbage collection cycle. Access to the pool requires locking. So if you're going to be using lots of threads all trying to access the same pool, then you're going to be having lots of contention, there may be blocking involved, and you might have a degrading performance in respect of that. Scalability in terms of the number of threads becomes a significant issue. If you're not using large number of threads, then it's not so much of an issue. And if you can manipulate those threads in a way that means that they're not in contention for the collection or the pool at any particular time, then you can minimize the impact of that. So what you're going to do is weigh up the benefits of large object allocation at startup versus the downside in terms of scalability for multiple threads and the contribution to the complexity of the scene graph. So it's really a balancing act. Third thing in terms of garbage collection friendly programming is about finalizers. And finalizers, the simple rule is don't use them. That's not I mean, it's a rule which is a good rule to go by, but obviously there are situations where you might think, well, I really do need a finalizer for this. Well, yes, there may be some very rare occasions where finalizers are actually valid and really do make sense, and you can't do anything other than use a finalizer. But really, really do think very hard before you use a finalizer, because finalizers have a really significant impact on performance. If you use a finalizer, you have to go through at least 2 garbage collection cycles in order for the object that has the finalizer to be collected, because the object has to be placed on the finalizer queue, and the finalizer queue will not necessarily run every time a garbage collection cycle runs. It also slows down the garbage collection cycles because we now do have objects on the finalizer queue and there needs to be processing of that and so on. So if you can avoid using a finalizer in terms of having that happen automatically, it's much, much better to use an explicit method that you create in your code and which you explicitly call when you no longer want that object to be used. So before you remove your last reference to that object, you make sure that you manually call the method which cleans up the resources. That way you're not then forcing a finalizer on the garbage collector. It's treated just as if it was a normal object, and so there's no impact from the concept of having multiple garbage collection cycles involved and the finalizer queue involved. Reference objects, where you're dealing with soft or phantom references and those types of things, are a possible alternative to finalizers, but as an almost last resort. An important note about soft references as well is that the referent is cleared by the garbage collector, and so this is how the garbage collector treats the references that you're declaring as soft. How aggressive it is in terms of reclaiming those objects is down to the garbage collector's implementation. So you're really placing your trust in the way that the garbage collector works. You don't have strict control over how your soft references actually get used and how they will get garbage collected. So the aggressiveness of the garbage collector will dictate the level of object retention. And there's no easy way of tuning that within the virtual machine. So certainly these are things to bear in mind very carefully when you're interested in very low latency, because these are things which again introduce this concept of non-determinism, because you can't predict what's going to happen with the soft reference. If you know in great detail how the virtual machine works and how the implementation of the garbage collector is going to handle these references, it might be possible to try and model that. But on the whole, you're really introducing non-determinism into your application through that. There are some other things around subtle object retention. So going back to finalizers, let's look at this class here. So I have a class which implements something and then extends a class which has a finalizer. So because we extend it, we get the finalizer as part of this class. Even though we haven't declared it within the class, we actually are subject to having a finalizer run on these objects. If I then declare a variable within this class, which is a large buffer, 2 megabyte buffer, what's going to happen is that that buffer is also going to be subjected to the garbage collection impact of the finalizer in the superclass. We can't avoid that because the superclass has the finalizer and therefore it must be called. We hit this minimum of 2 garbage collection cycles to free up that 2 megabyte array in non-determinism and so on. So what we could do is we could break some of the pure object-oriented approach and say, okay, rather than subclassing the class with finalizer, we'll encapsulate it as a reference. We can use that within our particular class. We can have our buffer within that class. And now, because we're not subclassing the class which has the finalizer, when our class, my implementation, is ready to be garbage collected, only the reference to the class with the finalizer will be placed on the finalizer queue. The buffer that we have of 2 megabytes will still be able to be garbage collected straight away because it's not being affected directly by the class with the finalizer. A couple of other things about object retention. This is a fairly minor point. Inner classes have an implicit reference to the outer class or the outer instance. So this has an impact in terms of the object retention, more specifically the graph complexity. Because now we've got extra references, the garbage collector needs to follow all of the references from different objects within the heap that are still valid. So inner classes will have a reference to the outer class. The garbage collector has to follow that reference to ensure that the class is still the reference to that class is still recorded. So effectively what this can do is lead to a potential for increased garbage collection, so increased latency. This is one of the nice things with Java SE 8. With the future of Java SE 8, a lot of inner classes will be replaced by lambda expressions. And because lambda expressions are not going to be implemented simply as a syntactic sugar on the compiler to simply implement those as inner classes, we'll be using the invoke dynamic bytecode instruction in the JVM, and so we can avoid a lot of this problem and we'll reduce some of the overhead of using what is in effect an inner class within the application. So let's talk about another approach to garbage collection. This is one that was introduced in the HotSpot virtual machine a while ago, and what we saw was that there were some limitations in current garbage collection algorithms. So concurrent mark sweep is very good in the sense that it can run concurrently with the application threads, at least in a large part of what it's doing. But it has some issues in that it doesn't do any compaction. So there's no compaction of data, which means we have to use free lists. We do have fragmentation of the heap. We also have need for a remarking phase, which introduces another pause, which is a stop the world pause. And so we can affect the determinism and we can affect the latency of our application. If we use parallel old, we can do full heap compaction, but the downside of that is potentially very long stop the world pauses. Certainly for low latency application, most full heap compaction is going to be way, way longer than any latency that we're looking at in terms of our goals. Now, we can potentially set a pause target for the concurrent mark sweep collector, but it really is a best effort. There's no guarantee, and there's nothing that the collector can do internally that can really affect it beyond sizing of the heap space and the different generations. There's nothing it can do as it's running to try and reduce the time that's required for particular parts of the garbage collection. So as we increase the size in heap, as we increase the throughput, as we increase the live set data, then these problems all start to show themselves. A number of people within Sun at the time and subsequently Oracle came up with the idea for the garbage first collector, which was a different approach to how we do collection of the old generation and in fact the young generation as well. So I'll talk through how that actually works. So from a kind of high level perspective, it's a replacement for the concurrent mark sweep collector. It's available as a fully supported usable collector from the Java runtime version 7 update 4 onwards. Prior to that, it was part of the HotSpot virtual machine, but we were using it as an experimental option. Now we actually support it as a runtime option, and it can be used in production systems. It's very much a server-style garbage collector, so it is aimed at server, long-running applications. It works in parallel, using multiple processors. It runs concurrently with application threads. It is using a generational approach, in the same way that we've seen with the HotSpot heap layout. So we have the concept of a young generation, we have the concept of an old generation. It is designed for good throughput, so we're not minimizing throughput, or we're not changing throughput at the expense of latency. However, the differences are that this is actually compacting, or strictly speaking, I suppose you could say it's semi-compacting. It has improved ease of use, so we're not looking at as many variables to tune in terms of changing what can actually be done, and it has more predictability around the pauses that you have with the collector, although it's not hard real time. So even though we can give better predictability, we can give better approaches to the targets that we're setting, we're not dealing with hard real time where we guarantee that certain things will happen at specific times. From a high-level overview of G1, it is a region-based heap. So we still have the concept of the young generation, we still have the concept of the old generation. The sizing of the young generation is dynamic, so it will actually change as the application runs. And then we do partial compaction of the heap space using what's called evacuation, and I'll explain that as we go through. The way that it works internally is it uses a thing called snapshot at the beginning. And what this does is it avoids the idea of the remarking phase that we would have in the traditional concurrent mark sweep collector. Again, how this works will become apparent when I talk through the diagrams that I'm going to show you in a moment. In terms of having a target for our latency and the maximum pause that we want to live with, what we can do there is we can actually tune things as the system is running. So we can look at the number of regions in the heap space that we're working with, and we can decide how many of those in order to collect in order to hit the target that we're aiming for. So rather than just being able to change the sizes of the parts of the heap, we can also adjust how much of the heap in effect we're collecting as the system runs and as the garbage collector runs, and that way we can adapt to changes so that we can more precisely hit the goal that we're working for. So the idea of calling it garbage first is that we always look for areas of the heap space that have more garbage than anywhere else. So by picking areas that have more garbage, we can be more efficient in terms of the amount of space that we can actually reclaim. So that's all very good. And we can also use things like minimal work for maximal return. So the amount of work we do, which again will become apparent when I talk through the diagrams. So for the next few diagrams, what you need to understand is that the colour scheme represents certain things. So here's the colour scheme that we're going to use. Grey represents non-allocated space. Green is the young generation, blue is the old generation. Light green and light blue represent the old generation, the young generation, and then dark green and dark blue represent recently copied objects in those generations. As the diagrams are shown, it'll become very easy to see how this works. So let's look at the young generation collection, or minor garbage collection, that happens using a concurrent mark sweep collector. So you can see that at the top of the diagram here we have the green areas, which are the Eden space and one of the survivor spaces. The other survivor space is empty, so there's no allocated objects there. The old generation has blue areas in it, which is the live data, and that's dispersed through the heap because we don't compact. What we need to do now is, because we filled up the Eden space, we need to run a minor garbage collection. And so we need to do some collection, we need to move some objects around. What happens is at the end of the collection, we've moved any of the live data from the Eden space and any of the objects that still need to be retained in the survivor spaces into the second survivor space. Any objects that needed to be promoted have been moved into the gaps that we had in the old generation. So we can see now that we've got some dark blue objects which represent the objects that were just promoted from the young generation into the old generation. If we look at this from the perspective of garbage first, what's going to happen here is that rather than dealing with physically contiguous areas where we can say, well, this is the young generation, that's an area of memory that we have, this is the old generation, that's an area of memory we have. What we deal with here is logically regions. So we say, okay, we'll break up all of our heap space into regions, and those regions can either be young generation or old generation, and they can be Eden space or survivor spaces. But they're 1 megabyte in size, which seems quite small, but there is logic behind that, and we'll explain that as we go through. So we split the whole of our heap space up into regions, and then we allocate those regions to be either part of the young generation or part of the old generation. And so we deal with a logically contiguous area of memory rather than a physically contiguous area of memory. So here we can see we've got some green areas which represent the regions being used for the young generation. We've got some blue areas that represent the regions that are being used for the old generation. We need to run garbage collection because the effect is that we've reached the end of our Eden space, so we need a minor garbage collection. What happens during the minor garbage collection is that we go through any objects which are still live data in the Eden space and any objects that are still any objects that are live data in the Eden space need to be moved into one of the survivor spaces. Any objects that need to be promoted from the survivor space into the old generation can simply use another region within our heap space. So we know which ones are empty. We can simply take one of those empty regions and start using that to promote objects into. It may have been used for the young generation before. Now we're simply saying this is now part of the old generation, and so we can add objects to that. So we're evacuating objects from the young region into the old generation. And the net effect is that we have the same thing happening. So now we've got our Eden space empty, so all of the regions that were being used for Eden space now are empty. Our survivor space has switched to the other survivor space in the same way we saw in the earlier diagram, and that's got some live data in it. And the objects that have been promoted into one or more regions which are now being used for the old generation. Now, in terms of the sweeping and the marking thing, what happens here is that if we need to do some concurrent work in terms of running the garbage collector on the old generation, concurrent collection has a number of phases to it. So what we have to do is we have to do an initial marking phase where we look at all the live objects that we directly reference from our application. We then have to go through and follow all of those references to map out the graph of live data, and we can do that concurrently. So we have an initial marking phase where we pause the application, track all of the application direct connections to objects, then we allow the application to continue, we do the concurrent marking. When we finish that, we then have to go back and remark because there will be some changes that have happened during the concurrent phase, and then we can go through and do the sweeping of the objects that are no longer required. So the net effect is that now we end up with a number of areas being added to our free lists, and we clear out the data that's no longer required from our old generation. From the point of view of the garbage first collector, things are a little bit different, and they make life a whole lot easier, because what we do in the evacuation pause, so our minor garbage collection, is we don't just go through and copy objects from the young generation to the old generation. We also look at the regions that we have for the old generation, and we look for we do some initial marking on that, so that we can build up a list of regions that still have live data in them, and then we can sort that based on how much live data they have. And the idea here is that when you do the concurrent collection, where you're looking through to say, okay, we need to collect data, or you need to collect garbage from our old generation, what's going to happen is that by using small regions of 1 megabyte, lots of those regions will be completely empty because the data in them will no longer be valid, and so we can instantly reclaim those spaces. We don't have to do anything, we don't have to move any objects around. We can simply add all of the regions that no longer have any live data in them to our list of free regions that we can use either for the young generation or the old generation. The other thing we can do is where there is still live data, we can sort those based on the percentage of live data that's still there. And that way, when it comes to collecting, we know that where we do have to copy objects from one region to another, we can pick on the ones that have the smallest amount of live data. So the amount of data we have to copy from those regions is as small as possible. And then if we pick on, let's say, 10, each of which have 100k of live data, we can copy the 100k of live data from each of those 10 regions into one region, which is 1 megabyte in size, and have that region completely full. So we've effectively compacted the data into one region. We then free up 10 regions which now don't have any data in it, and add those to our list as well. So at the end of the remarking phase, we simply say, okay, now we've collected all of our regions that don't have any data in, and we've actually then compacted, so pick on the live ones, the ones with low amounts of data, and we end up with an effective compaction into a smaller amount of space. So if we look at the comparison between concurrent mark sweep and the garbage first collector, the layout of the heap is logically the same. So we're still dealing with young generation, Eden space, survivor spaces, and an old generation. But from the point of view of the layout of the heap, it is very different. By using regions in G1, where we're not dealing with contiguous memory, we can then choose where to put data and do that dynamically as the system is running. We can also pick on regions that have small amounts of live data to maximize the efficiency of the garbage collection as we're going through. Now, latency is a key goal for Oracle, and so our engineers are very much looking at this in terms of, okay, we've got G1, that's one approach, but what other things can we do in terms of improving the response time, reducing the latency associated with the virtual machine? There are a number of areas of research that are going on at the moment. We're looking at lots of different ways of doing this, and at the moment we're looking at all these different ways with the idea that we'll pick the most efficient ones, and we'll implement those at some point in the future. So we're looking for requirements, we're looking for what customers are actually interested in from the latency perspective. So having spent a lot of time talking about virtual memory or memory management within the virtual machine, let's talk a little bit about adaptive compilation and some of the impact that we can have in terms of latency around using the adaptive compilation. Now, basically what we're dealing with here is the concept of a just-in-time compiler, where pieces of code are being compiled as they're required by the virtual machine. So we have a set of bytecodes that need to be interpreted, and at some point the virtual machine is deciding that a particular region of code is being used sufficiently frequently that it makes sense to compile those bytecodes into native instructions so that we don't have to continually convert those bytecodes into native instructions every time we use them. This would be the typical situation of using a loop many times. Now, the thing is that with what the virtual machine can do is make decisions about optimizations based on what is happening in your application. So the only data that the virtual machine has available to it is what has actually happened from when the application started running to this point in time. So it knows exactly what classes have been loaded, and it knows what code paths have been executed so far. But it does not know about all the code in the application, because it doesn't know about any classes that haven't been loaded. It doesn't know about all the possible code paths that could be used by this application, because many of those haven't actually been executed at this point. So unlike a traditional compiler, which will look at the whole application, every single piece of code that's possibly used by that application, the JIT compiler only looks at the code that has been run so far. The optimization decisions of the JIT compiler have to be based on the runtime history. So it can only use what has happened in the past to decide what to compile. It has no ability to predict the future, so it doesn't know what's going to happen moving forward. And what that means is it can make some decisions which are not going to be great, because if you've been running a particular loop a number of times and it gets to the point where the JIT compiler says, that loop has been run enough times that it makes sense to compile that set of bytecodes. If you then immediately stop using that loop, you get to the end of the loop, then the compiler has compiled a set of bytecodes for no benefit. So that kind of limits some of the optimizations that can be used. As the profile changes, then the JIT needs to react. Your application may change the particular paths that are being used. Different clients may use different options within the application, different things may need to be processed, and you go off into different parts of the application. So the JIT compiler needs to then say, okay, I don't need this particular bit of compiled code anymore, it hasn't been used for a long time, so we'll effectively drop it out of the cache, and we'll re-optimize based on the new profile of where the application code is going. Now, from an internal profiling point of view, what the system needs to do is determine which methods are hot and which methods are cold. So which ones are being used lots, which ones are not being used. And there's different ways of doing that. You can either do it in terms of looking at everything that happens, where we're looking at invocation counting. So what that will do is it will simply say, every time a method is called, then we record that as a count. So we know exactly which methods are going to be the ones that are being used most and the ones that are being used least. We can do that by adding an add instruction into the native code, and we can simply say just increment a counter every time we call that. The other way to do it is to do it on a periodic basis, where we do thread sampling. So we say, okay, every 100 milliseconds or every 50 milliseconds, we look at all the threads that are executing, and we say which piece of code is each thread executing at that point, and we record that detail. So we're doing more of a statistical sampling rather than a full set of information. By doing that, we can minimize the impact that it has on the actual code, because we're not looking at every single method call. We're doing a periodic check, and so it's minimizing the impact that we have. The third approach is to use hardware-based sampling. And a lot of platforms nowadays have program counters and different statistical counters that can be used by the hardware. And that, again, will minimize the impact because you're using them at the very lowest level. And so we can use instrumentation mechanisms in order to do that. So there are some assumptions that the JIT compiler will make. The first is that methods will probably not be overridden. Now, that's not to mean that you never override methods, but on the whole, you can make an assumption which says methods will not be overridden. And by doing that, you can improve efficiency. Yes, many methods will be overridden, but that's in effect, it's an exceptional circumstance rather than the common case. So by doing that, we can improve efficiency. The other thing is floating point numbers. So we actually make the assumption that a floating point will never be not a number, so an unrepresentable number. And to do that, or to process floating point numbers, we actually use hardware instructions rather than the floating point library. So where we can use the floating point processor within the hardware, we can do things more efficiently rather than doing it in software. So we make that assumption unless a floating point value is set to not a number. Exceptions are the exception. So what we say is that for a try catch block, every catch block is very unlikely to happen because we hope that exceptions don't occur. So what we do is we always mark catch blocks as being cold. We may well compile the code in a try block, but we will always say, oh, the code in the catch block is going to be marked as cold because that is the exception to the rule, not the normal situation. Locks will probably not be saturated, as in used excessively. So what we do there is we say, okay, for a lock, if we want to use a lock, then we'll start as a fast spin lock, because the chances are that by spinning the processor for a number of cycles, the lock will be freed, and so we'll actually be able to acquire that lock. Rather than changing context, shifting out registers, writing out the context of the thread at that point, and then loading another one, what we do is we say, okay, give the lock a chance to be unlocked by spinning the processor, and chances are that will happen. The other thing that we do is we work on the principle that most locks are acquired and released by the same thread. And so if you've got a thread that's processing something in a collection where the collection has synchronized methods, chances are that when you iterate through that, same thread is acquiring and releasing the lock on the same collection, and so we can replace that with a no-op, because we can say, well, okay, if it's the same thread releasing the lock and then acquiring it slightly later, there's no point in releasing it and then reacquiring it. We can simply just ignore that unless another thread comes in, at which point we have to do extra work. But from the point of view of efficiency, we can simply assume that for the majority of cases, most locks will be released and acquired by the same thread in a particular number of situations. Inlining and virtualization, these are competing forces. So the most effective optimization that the compiler can do is method inlining. Rather than the compiler having to resolve methods, call a method via a lookup, call a method via a reference, and then put things onto the stack, make the method call, pop results off the stack, and so on. What it does is it simply takes the instructions that are in that method and places them where the method call would be. It makes the code bigger, but it makes it run much, much faster. Problem is that by virtualizing methods, which happens a lot in Java, the way of method inlining becomes problematic. So from the good news point of view, JIT method or JIT compiler can devirtualize methods. So if it only sees one implementation of a particular method, then it effectively says, well, it's not a virtual method, so we will treat it as being monomorphic because there's only one implementation, therefore it can be treated as a single method. Bad news is that if the JIT compiler later discovers that there is actually an additional implementation due to subclassing, and the reference that you have is to the superclass, then it needs to de-optimize the code, it needs to undo the method inlining that it's done, potentially re-inlining the code, and so it would need to re-optimize it to make it a bimorphic call, because there's two implementations that can be used. And certainly if you go off into the idea of having third or more implementations, then you end up with a multimorphic call where the JIT compiler is quite limited in what it can do from a performance point of view. Again, some important points about inlining and virtualization. Implementation changes during steady state. So what you don't want to be doing is to making changes to the way things work from a class structure point of view once your application has reached its steady state. So you don't want to be using different subclasses from the point of view of virtualization once you've reached the steady state. Should you write JIT-friendly code? We talked a lot about the idea of garbage collection-friendly code. Should we write JIT-friendly code? Well, actually, no. I mean, in this case, you should really let the JIT figure it out, because the JIT is pretty good at analyzing what's going on in your application. There's not really many situations where you could make a significant impact on what's actually happening with your code by writing your code differently from the JIT point of view. So do beware premature optimization. Don't do it. Code naturally and let the JIT figure it out for you. If your application has performance problems, you need to profile it, and then you need to find out where those problems are, and then you modify code, but only for the problem areas in order to improve performance. So don't be thinking about how the JIT compiler is working when you're writing your code. Wait until you've got your code working, you've got the algorithms all sorted out, and then if you've got performance issues, work on those in terms of improving efficiency. So basically, to conclude this session, the Java applications use a virtual machine. We have the JVM. So we need to be aware that there is automatic memory management, and we need to be aware there is adaptive compilation of bytecodes. Now, how these things work does have a significant impact on the performance of your application. How your application interacts with the JVM from the point of view of memory management and of adaptive compilation can radically change the performance profile of your application. Having said that, of course, what you need to do in terms of tuning an application is to profile, profile, and profile. You've got to know what the application is doing in order for it to be able to, or in order for you to be able to understand how to improve the efficiency of it. Avoid premature optimization. Don't be thinking about the fine details when you're writing the application. Yes, be aware of some of the issues, certainly around memory management, use of finalizers, and so on, but don't be thinking at the very lowest level in terms of JIT compilation and so on as you're writing your code. Place to go for some more information. There's a couple of references on the Oracle Tech Network. There's some good articles about tuning of the virtual machine. There's a nice document that's available from Middleware Magic that was written about WebLogic and talks a lot about some of the JRocket side of things. I've spent a lot of time talking about HotSpot. In this paper, they also talk a little bit about some of the JRocket specific things that are going to be integrated into the HotSpot virtual machine moving forward. So with that, I hope that you have enjoyed this session and that it has been useful for you. So thank you very much.